Today's lecture I will start nodal analysis. Nodal analysis means first you have to understand the wellbore performance, how fluid is flowing from reservoir to wellbore to the surface separation system. Now to understand this one, first I have to draw the wellbore system. So let's say this is wellbore and this is one tubing and there is a packer and there is perforation. Perforations will be like this. Sometimes we draw like this, sometimes we draw perforation like this. Okay, so whatever method you use uniformly like this. Okay, so anyway you can draw your perforations. Now this is your reservoir, assume. Reservoir means lots of connectivity will be there, lots of liquid, sand, fluid, everything will be there. All right, and this is your casing. And on the surface what happens, your tubing is going there and there will be first one valve will be there. Okay, so there will be control valve, then there will be choke. Choke is drawn like this. Choke means you are restricting flow. Okay, then from choke the fluid will be going through maybe little bit upward direction or maybe downward direction, then your fluid will reach to separator system. Separator gas will be separated and liquid will be separated and you are finally reaching to stock tank. Okay, and sometimes the wellbore can be horizontal or slanted like this. Like this, the wellbore can be like this. Okay, and it can be like this, and there will be packer again, and there will be perforations, and your reservoir will be connected through wellbore. And I already explained why there will be vertical or wellbore and horizontal wellbore. Horizontal wellbore you are going if your pay zone thickness is very small and is very wide. So in that case what happens, if you have only this much of your perforation zone and pay zone is very much wide all around, then you are getting connected only this much amount. But if I make wellbore horizontal, so if you are making horizontal, what happens, you can connect lots of area of pay zone area with a wellbore. So more fluid will be entering into your wellbore, so your productivity will be increased. That's why we go for horizontal wellbore. Okay, but for simplicity, for our nodal analysis and other calculation, we assume that it is vertical or almost vertical wellbore. Okay, but if you go for detailed analysis for horizontal wellbore, multilateral wellbore, that will be different course actually. That will be multilateral drilling and production course. So in this course I am not going into that much of difficult or complex situation. So whenever you are talking about node analysis, then you have to consider node. Node means, let's say reservoir pressure PR. So sometimes we say reservoir pressure PR, sometimes PI, sometimes PE, sometimes P bar. So all notice will be almost similar meaning. So we are assuming that is reservoir pressure. Okay, and when fluid is flowing from reservoir to your wellbore, so there will be PWS or PWFS. We say this one is sand face completion area. So from reservoir to near wellbore it reached. So how much resistance it got, we have to calculate. Okay, from there again fluid will be entering into your wellbore. There will be PWF, flowing pressure. Okay, the term is flowing pressure. This is reservoir pressure. This is flowing sand face pressure, or just entering to the wellbore the pressure. Sand face pressure. This is flowing pressure. Okay, now there may be some artificial lifting mechanism or some restriction. So there will be again certain losses. So there will be we can say P pump or something, some term we can give. So there will be another node and there will be like artificial lift, maybe artificial artificial lift, L-I-F-T, and there will be another blockage area here. This is called safety valve, S-A-F-E-T-Y, safety, S-A-F-E-T-Y, safety valve. Why safety valve will be there? It will be under the surface actually. What happens when you are producing oil and gas? So if sometime earthquake occurs, or sometime let's say terrorist attack occurs, or some cyclone occurs, because of that your wellhead gets broken and flow is uncontrolled. In that case, this subsurface safety valve, normally this is called subsurface safety valve, subsurface safety valve. In subsurface safety valve, the one pressure line goes to the upper up to the wellhead and Christmas tree. So if somehow Christmas tree gets broken and flow is uncontrolled, what will happen, that one small pipe is going to control the subsurface valve. So that pressure will not be maintained because this upper surface is broken, or someone has taken away this wellhead or something, then flow is uncontrolled, and at the stage automatically this pipe, the pressure pipe will be cut. When pressure pipe is cut, what happens, that pressure will not be maintained at the surface to control the valve. So the valve will be closing the path automatically. So it is called fail safe valve. Okay, this is called fail safe valve. Fail safe valve. Why fail safe? If something fails, the system must be safe. For example, if you see similar operation in railway tracks, like train bogies are connected one by one, and if you cut one bogie by some means, then automatically the cut bogie will reduce its velocity. Okay, slowly it will get stopped. If it is moving at very high speed, it can be dangerous. So that is called fail safe operation. If you cut it, vacuum pressure will be released, and at the same brake will be applied on the train wheel, the bogie wheel. So when brake is applied, it will be stopping gradually. So here also, if something occurs like terrorism attack or cyclone or anyhow your flow rate is becoming uncontrolled, pressure will be cut, pressure line, small narrow pressure line, and that pressure line will, when it is cut, pressure is not maintained to control the safety valve, and safety valve will be closing the flow path and flow will be stopped. Okay, this is called fail safe operation. Okay, and after that there will be one master control valve will be there in Christmas tree. If I already told that the Christmas tree will have several valves, lower control valve, upper control valve. So one will be automatic, one will be manual. Okay, so here I am not showing all the valves, but I am showing only one. So this will be one control valve, and next is choke. So control valve, actually you can control your flow rate. So if required, you can close the flow, or you can increase or decrease that portion you can do. Another part is that called choke. Choke. This is called control valve. Control valve. So what is the function of choke? Choke, actually it will reduce the flow. So wellhead pressure is something, and your separator system pressure will be something. So in between, choke will be controlling the flow and will give desired pressure and temperature to the separator system. Okay, so whenever you are thinking about nodal analysis, so you have to consider everything as a node. For example, choke is a node, your control valve is a node, and wherever the major pressure losses are there, you consider that area first. And other pressure area, loss area will be like tubing, like horizontal pipe or slant pipe is there. So there will be again pressure loss. In separator system, there will be again pressure loss. Finally, you are reaching to your stock tank condition. Stock tank condition means, I already told, this is 14.7 psi and 60 degree Fahrenheit in standard condition. But normally we say this is in normal environment, like whatever temperature is there in your atmosphere. So that will you have to maintain. So then for nodal analysis, you are calculating pressure losses at different points. Okay. So overall production system, I already told this wellbore. Again I will draw. Okay, this is wellbore, and I have one tubing. tubing will have packer, because annular area, this is called annular area, this is called annular area, annular area. So many times we do not use annular area, it will be just idle, or many times we use this one for injecting gas or some other fluid, or we can take some production also sometime. So but main production will go through your tubing, tubing also one metal pipe, all right. And we have perforations like this, again here another, this side also, because this is circular shape, so perforations will be all around, okay. But I am drawing in 2-dimensional figure, so we cannot show in all all directions, 360 direction. I am showing only the left and right side. Now fluid will be entering from reservoir, this is reservoir, this is pay zone. So in reservoir term, pay zone is actually where reservoir can be very big, but when you are drilling a hole and you are getting production from certain zone, so that zone is called pay zone, that is paying you, okay. And reservoir cannot be like purely straight line and rectangular shape or circular shape, it will be different random shapes, but for our approximation purpose, for our calculation purpose, we approximate, we assume this may be rectangular shape or spherical shape or different other shapes also possible. So because reservoir you cannot approximate like it will be completely rectangular, right, because the post can be extending from rectangular some side to another area, so that will happen. But practically when you are doing calculation, we approximate and we use this geometrical shape like spherical, circular, all the shapes we consider. Now one is PR, I told, PR reservoir pressure I said, and there is wellhead, all right, there will be wellhead, from wellhead it is going WH wellhead, so PWH wellhead pressure. So when wellhead you are considering, wellhead is having lots of flow bending, turning, valves, chokes, so that's why there will be lots of pressure losses. So whenever there will be any pipe flow, there will be losses. What are the losses actually? Later we will discuss in details, but here I can give some overview, like losses in pipes, losses in pipes or flow systems, So losses means pressure drop actually. When fluid is flowing through a pipe, there will be pressure drop, okay. So the pressure drop will be because of friction factor, see friction, narrow zone. So you are creating narrow zone because of you are creating choke. So because of choke, there is narrow section. Narrow section means pressure drop will be there, lots of friction will be there, and fluid velocity will increase, and you will get lots of pressure drop. And pressure drop can be there in sand face completion area, where when you are putting a sand control system means you are restricting flow. If you can restrict 100% flow, there will be no sand flow, but we want liquid flow or gas flow, and because productivity we have to increase, so that's why we give some pores. Through that pores, sand, oil and gas will come, at the same time some amount of sand also will come. So actually we are restricting the flow. So restriction, any restriction that will be giving your pressure drop. Then next is bend. Any bend is there in any pipe, there will be again pressure drop or pressure loss. If any sharp change in pipe dimension, for example, pipe initially is like this, horizontal, but suddenly increase or suddenly decrease, there will be again pressure drop. So sudden increase or decrease in piping diameter, sudden increase or decrease in piping diameter will give again pressure drop. Pressure drop can be possible because of your fittings, such as you have valve fitting or you have any joint. So there again there will be pressure drop, because the flow surface will not be smooth, there will be some protrusion or some cavity or dimple. So because of that there will be friction, pressure drop pressure drop. So major pressure drop occurs because of this sand control area or reservoir to your wellbore connectivity. So reservoir and wellbore connectivity, that is called inflow performance. Inflow is happening here, reservoir to wellbore, right? And this PWF or flowing pressure means when wellbore is flowing, you are getting liquid, oil or gas, that is flowing condition. So that when we are getting the pressure, that pressure is called flowing pressure. Okay, and if we stop the production, then flowing pressure will be 0. And if we assume that there is huge amount of flow is occurring, huge amount of flow, so in that case reservoir pressure and flowing pressure, the pressure difference will be very high. Okay, but if flowing pressure is very high, let's say almost equivalent to reservoir pressure, in that case there will be no flow because pressure difference is low. Because to flow fluid particle from one point to another point, you need pressure difference. If you don't have pressure difference, there will be no flow. So if we assume PWF and flow rate, so initially reservoir pressure is very high, okay, and your flowing pressure or your wellbore is not producing, your valve is closing the flow path, so there is no flow. So in that case, what is happening? Your PR and PWF almost equal, okay. So PR and PWF almost equal. So in that case, your flow rate will be almost 0. PR, okay, flow rate is 0. But in certain situation, if PWF is 0, say that wellbore pressure is almost 0 or completely 0. So in that case, your PR minus PWF is very high. PR minus PWF is very high. Okay, so if it is very high, in that case, if flow rate will be very high. Okay, so if wellbore the flowing pressure is 0, then in that case you are getting very high flow rate because the difference PR minus PWF is very high. But if opposite happening, PWF is 0, so then flow rate is high. If PWF is very high, almost equal to PR, so in that case you are getting Q0. So the curve normally it will be like this. Okay. Now if I get slope of this curve, if I get slope of this curve, the inverse of slope is called productivity index, okay, and this curve is called IP relationship. Inflow performance relationship or IPR. In generally it is called IPR. So IPR, if I see, if I assume this is x axis, this is y axis, so tan theta equals 1 by j equals this y PR minus PWF divided by Q. So J equals Q divided by PR minus PWF. So J is called productivity index. J is called productivity index. It should not be mixed up here. Okay. Now this is inflow, and another term is used called outflow performance. Outflow. What is outflow? When fluid or oil or gas entered into the reservoir, from reservoir to the surface separator system, fluid is flowing, so that is called outflow performance. And although we have defined upstream, midstream and downstream oil and gas, but here for specific nodal analysis we use upstream, downstream little bit different way. For example, I have one choke here, okay, I have one choke here. So for choke, this is upstream, this is downstream, okay, this is upstream, this is downstream. If choke is my node, then upstream of choke means before choke the fluid is coming, that is upstream, and after choke fluid is going, that is called downstream. Now main elements of the nodal analysis. So first again I will draw one figure, the same figure quickly I will draw, like I have packer, I have tubing, okay, from tubing my fluid is going like this, I have choke here, I am assuming there is no valve now, then it is going to separator, it is going there, gas, and I am storing a stock tank. Gas is going to compressor, it is, and again the liquid is being stored in stock tank. Now the main points are, this is reservoir will have like this. So reservoir PR, so this is from here we can start 1A, this is 1, it's the separator system is 1, then there is 2, then wellhead is 3, then there will be another valve arrangement, this is 4, then there may be one pump here, 5, pump or artificial lift, we call artificial lift, this is called pump, and then there will be reservoir connectivity 6, then sand phase completion 7, then reservoir area 8. So there are key points of for the nodal analysis, because we have to find where the pressure drop happening and where the maximum pressure drop happening, whether can we again when we are calculating pressure drop, we have to consider from reservoir to the separator system, we cannot analyze separately. So for example, if we calculate inflow performance relationship, at the same time we have to calculate outflow performance relationship also, because everything is linked. We cannot say like inflow is there and you are calculate separately that one. Then if there is mismatch between flow rate and pressure and temperature, everything, then actually your whole system will get disturbed, you may not get production, or your production can get hampered. So your pressure drop is like this, like if it is PR, this is PWFS, PWF, then okay, so many I'm not writing here, maybe here P4, PW and P pump, okay, P here I can write like P safety valve, P safety valve, P wellhead, PWH, P choke, P separator, something like that. So pressure drop del P first pressure drop can be like this, PS minus PCH, PS which is higher, PCH is higher, so PCH minus PS del P2 equals PWH minus PCH. So in that way we can calculate all the pressure and how the pressure varies from reservoir to the surface. Okay, so first reservoir, then tubing, major losses I am trying to show, flow line, then transfer line. So let's say initially reservoir pressure is very high, PR or PE, whatever you say, then through porous media there will be certain losses, and when it is entering into your wellbore, so there again some pressure drop will be there. So from wellbore there will be some pressure drop in tubing, and when it is reaching to wellhead again there will be certain pressure drop, flow line there will be certain pressure drop, again it will be pressure drop, and finally it will go like this. P stock tank. Okay, and this is reservoir pressure, and PWF, this is PW wellhead pressure, and then P separator, sorry, PCH. I said like choke, this is choke I can say. So, choke pressure. So, that way the pressure will go down. So, if you want to reach stuck tank, then we have to see where the pressure loss is maximum, how to avoid that one. That also we have to consider during design selection, design stage of the whole system. Okay, now we have seen IPR curve like this. Initially we are assuming this is a single phase flow, or single phase flow, single phase liquid. So, in single phase liquid there is no phase change occurring from reservoir to the wellhead, let us assume. Okay, and flow is like this, Q is here, Q max, and this is PWF, P reservoir. So, sometimes people will be writing PR, P bar, or PE, PI. Okay, and Q, sometimes they will be writing small q. So, whenever you are writing any unit, you should write, you should explain what notation you are using for which purpose. For example, reservoir pressure, if you are writing PR, so you write reservoir pressure equals PR. And units also you have to specify. If you are using field unit or SI unit, does not matter, you have to use, but I will ask you to use field unit, because you have to be familiar with field unit, because whenever you are going for an interview or any interacting with other industry professionals who are working in the oil industry, so they will understand field unit basically. If you say kg per meter cube for density, then they will think, oh, how much this one, but if you say API, quickly they will understand, because they will be very much familiar with the terms. And terms, sometimes this field unit terms also we use different way. For example, barrel, if you take barrel, I already explained BBL, blue barrel or barrel. So, if barrel per day production we write, then sometimes we write like B barrel per day, sometimes BOPD barrel of oil per day, sometimes BWPD barrel of water per day, sometime BL per day, sometime BBL/D, sometime only BD barrel per day, sometime stock tank barrel per day, STB per day. So, several way we use. So, if I write BBL per day or BOPD, so you have to assume that okay, this is a barrel actually and per day. And if you are not using per day, then you have to specify actually it is hour or minute or second, but normally barrel per day is the common notation for flow rate. Now, this is inflow performance, and there will be another curve called outflow performance. Outflow, inflow. In the next lecture, I will try to explain the inflow performance in details, and outflow performance also will be discussed in the next subsequent lectures. So, inflow performance, if single phase is like this, if we have two phase flow, then it will not be straight line, it will be like this, or it may like this. Okay. So, there will be different relationship I will discuss later. And for outflow performance also, if we have multi-phase flow or single phase flow, we have choke and choke conditions are there. So, that discussion will do later, and basically this will be our production area. So, this production area does not mean this is optimal or something. This area shows, or this cross area shows that production is coherently happening all from reservoir to the stock tank, and there is no issue. But if you deviate from this point, then there will be problem, because maybe you will try to produce very high amount of fluid, but other systems are not matched properly. So, in that case your whole system will get disturbed and you may not get proper production. So, Q max Qmax means when I already told that when flowing pressure you assume it is 0 ideally, but normally it will not happen if you are producing continuously. But if you ideally if it is 0, then you will get very high production. So that outflow performance sometimes it called vertical lift performance also. So if you are getting different terms, so you should not get confused that it's not taught or it is a different term, I don't know. It may sometimes they call vertical lift performance, vertical lift performance or VLP. Okay, whenever you are talking about talking about nodal analysis or IPR or VLP, you should talk about pressure, temperature, single phase flow, multi phase flow. That's why I taught already that part, reservoir flow property, fluid property, so that you should understand fluid properties units. Then you try to correlate reservoir pressure, how much is there, how much fluid is coming. Then if this much of fluid is coming, and if you are putting artificial lift, whether gas is generating or it is having lots of sand, or pressure drop is very high, if you put pump, then there will be actually cavitation. So that sort of issue may come up. So if you understand this IPR or VLP or outflow performance relationship, then actually you will be able to select proper artificial lifting systems for your wellbore.